Good morning or good afternoon, wherever you are. This is Mo Ehsani, and welcome to our podcast. This is episode 6 in our third season of these podcasts. And as you've noticed, we have made a little bit of a change. We started this podcast series as being marine infrastructure live, but as you know, and we've done about 25 or so podcasts, I think, just focusing on marine solutions. But then I realized that there are so many other applications of FRP that our company is involved with, and I think even as our viewers yourselves, perhaps if you're a consultant, engineer, or a contractor, you may also be interested in all of these other applications of FRP products. So we've change it into, just from here on, the podcast series will be basically on all kinds of infrastructure repair, but primarily using FRP. So for those FRP enthusiasts, you're still going to get your dose of FRP. And with that, let me just start with our presentation for today. So I thought, for this first non-marine presentation or podcast, we'll do two two podcast series. So this is, we'll be talking about repair of culverts, and there are, this is a two-part. So today, this, as you show in here, we have, today we'll be focusing on the upper half of this, which is the repair of rectangular box culverts. And there are a couple of techniques that we can use with that, either the wet layup or using the SPiRe Plus panels as another way. And then on the next month in November, we will do a podcast on repair of culverts using, our other approaches, such as, StifPipe or gunite and wet layup. Those are primarily good for corrugated metal pipes, where you have usually a circular or even non-circular shape. So those would be the focus of the next series. So the wet layup system that we are talking today about, starting with that for repair of these culverts, this is really I call it the old version of the FRP, or the DOS version, the landline, if you want to compare it to the phone system. So this is something that we introduced in the 1980s. I know some of you may not have still heard of it, but believe me, this is more than 40 years old now. So we introduced this in the 1980s, and basically what you do, you use either carbon or glass fabric. And I don't know if any of you actually have seen this or not, but this is like, what I'm holding. This is a piece of carbon fabric, about 6 inches, 8 inches wide, but they come in, different widths, and as you see, it's very flexible. So with the wet layup system, we saturate this fabric with epoxy in the field and apply it to the structure, almost like a wallpaper. It goes on fairly easily, and by the next day, when this resin cures, you get a product which is, the 2 to 3 times stronger than steel in terms of its tensile strength. And this has become really a commodity. You'll find many companies, they sell, like Sika, Master Builders. There are other companies that some of you have used, maybe Five's products, but there are many companies that sell these, the old system or the fabrics. But depending on which company you go with, in terms of their level of engineering support, you'll find out that they vary, and in some cases they offer really almost no engineering support, so you're on your own to design with this. Now, the wet layup system by itself, it has a few advantages and a couple of disadvantages. So the advantage is that the fabric conforms to the geometry of the structure. Now, I know on the example today, maybe this is not that critical. We were talking about a box culvert where you have a flat slab basically that we are strengthening. But if you have, think of, for example, repairing an ASHTO girder where you have a, you know, bulb shape, you know, difficult to form geometry. And in those cases, the fabric easily conforms around the shape of that ASHTO girder, for example. And then each layer of the fabric that you see here, each layer, by the time you saturate it with resin and apply it, it's about 0.05 or, you know, a little bit over 1 millimeter in thickness. So um, it even if you add one or two layers of it, you can see that you add very little to the thickness of your original structure. So in case of, for example, repairing a culvert, it is not going to reduce the capacity of the culvert by adding a thick repair system to it. In fact, in many cases, because of the fact, you know, the surface of this FRP is so smooth, it has less friction, and in many cases, even if you're reducing the cross section a little bit, but you still get more flow through it than what you started off with. The disadvantages of the wet layup system, a couple of main ones, are that you cannot apply that to a jagged or rough surface. The surface of the concrete, for example, is corroded. You must first repair that concrete, patch it, make it smooth, and then apply the fabric to it. And you know, this is one of the shortcomings of it. And the other one is that it cannot be applied in wet or underwater conditions. Um, you know, if you're really good at it and there's some tricks, maybe you can apply it in some cases. But if you have, for example, a culvert where it is always water is flowing through it, or, you know, then this is not the best way to repair those. So the uh, just kind of like, maybe for some of you this might be a review, but the term FRP, the acronym FRP, stands for fiber reinforced polymer. And if we break it down, so you have a polymer that I'm showing here in red. This polymer could be epoxy or vinyl ester or polyester matrix. And that polymer is being reinforced with these fibers that are shown here as black dots. The fibers could be, you know, carbon or glass for the most part. For structural applications, they're either glass or carbon. And the one of the differences, so the matrix or the polymer serves two purposes. It protects the fibers from abrasion or damage. So it provides some kind of like physical uh, protection for the fibers. And secondly, it distributes the loads uniformly among the fibers. So that's really one of the main benefits of that resin matrix. Now, one of the things that is very different when you compare FRP products to other engineering materials is that FRP products, you know, like if you take a steel plate, for example, if you pull it in X or Y direction, you have the same tensile properties. That's an isotropic material. FRP products are anisotropic, meaning that the strength of the laminate is not the same in X and Y. It depends on how much fiber you have in any given direction, because remember, the fibers are the component that add the strength to an FRP. So this feature of it can actually be very useful in, you know, because you can orient the fabric or the fiber to get the most out of it. And if you don't need any strength in the transverse direction, then you don't put any fibers there, and that results in a more economical design. So these are like the typical original fabrics I was telling you. The carbon fabric, you know, is the black one is carbon on the left in this slide, and on the right you have the glass fabric, and then the various resins that get applied to them in the field. I thought, you know, this one quick video, it shows you let's watch this video of how we make with several bricks that are not joined together in any way, how quickly with this wet layup system you can make a beam out of it. So let's watch this video together. As you see, we are, cutting the length of the fabric to the length that we need. This first epoxy, which has a consistency like toothpaste, we call it a tack coat, that we put that first on the back of the bricks, spread that to, to get the brick kind of like make it, get rid of any of the sharp edges. And then here, so here he's spreading, putting that on the back of the uh, brick, spreading that, make it, getting rid of any of the sharp edges there. Then we take that band of fabric, and with that other resin, which is almost like warm honey, you roll or saturate that with resin and pick it up and put the fabric, saturated fabric, on the back of the brim. With your gloved hand, you can work out to get any of the air, rid of any air bubbles. This takes maybe about half an hour to make this sample. We let it sit in ambient temperature. The next day, you see, when you put the fabric in tension, you've built a beam out of it. And so now you can, it supports the weight of these four guys. And not only that, that same next day you can drive a truck over it, and you see that when when it fails, it's actually the brick that crushes, and not the, not the uh, carbon fabric. So this is kind of like the principle of how these things work. And just, again, I'm only really trying to show you the concepts today here. These are not intended for you to exactly follow in your design, but just to introduce you to these concepts. So this ACI Committee 440 that provides design guidelines for externally bonded FRP for strengthening applications. I am here showing you that, let's say if you have a slab or a wall that is reinforced with a number 7 grade 60 rebar, you see that every number 7 has a tensile force of 36 kips or 160 kilonewton. And then if you, for example, if we are using a particular carbon fabric, which is kind of, similar to the one that I'm showing you here, actually, this is more or less, the same type of fabric. So with that fabric now, you see, if we, uh, this fabric has a, if you made a coupon out of it and tested it in tension, every inch of that fabric has a breaking force of, let's say, 6,000 pounds per inch. So if we put this fabric now, on apply that to that, compare that with that, or put that on that wall or slab, you see every 6-inch strip of this fabric gives you the same 36 kip force as one number 7. So one way to compare it is, you could say that one layer of this particular fabric is equivalent to number 7 grade 60 rebars placed at 6-inch on center, because then you get the equivalent force. But of course, you notice that putting this fabric on your structure doesn't add any weight or thickness to the structure, and also it is much easier to install. I already mentioned, some of the, again, the advantages of this system, that you have high tensile strength, lightweight, they don't corrode, they last forever, and they're easy to install. And one benefit of this wet layup system, or in general, really all of your FRP products, is that if you apply them to the entire surface, you create an impervious layer that keeps moisture and oxygen away from your structure. So it kind of brings the corrosion process to a halt, because remember, for corrosion to take place, you need oxygen present. And if you stop that flow of oxygen, then you have actually shut off the fuel to the corrosion process. Another thing that I always remind people, that I know sometimes our environmentalist friends complain about these plastics that we throw in landfills. They last forever, and they don't decompose easily. That's true, and I hate to tell you, but these FRP products that we are talking about here are even a lot more durable compared to your plastic milk cartons, because the resins that we use are a lot more stronger and durable. And the fact that they are reinforced with these fibers, it means that they don't break or peel off that easily. But hopefully we can all agree that if there is one application where you don't want your materials to decay or decompose quickly, is when we are renewing our old infrastructure. So it's really a good application for these products. Now, I mentioned before, there are codes like the ACI Committee 440 has this code for, as you see, it's the design and construction of externally bonded FRP system for strengthening of concrete structures. They have another one for masonry structures, one for embedded, cast in place like rebar. But in this case, again, without going into the details of this, they basically give you, it's very similar to most of the other codes. You assume linear variation of, elastic behavior to failure, strains very linearly across the depth of your section. And, for shear, they specify a lower strain of 0.004, which basically ensures that your cracks don't open too widely, so you take advantage of that aggregate interlock component of shear. And then they have different environmental factors that you can apply. For example, whether the fabric is glass or carbon, they have different capacity reduction factors. Glass is given a larger reduction compared to carbon, for example. And then, the environmental uses of, or whether it is interior or exterior exposure, or whether it is an aggressive environment like, in a sewer pipe or what have you. So there are a lot of, these guidelines that you can follow. I wanted to show you this one project that we did in Phoenix several years ago. And maybe I'll show you this video and just pay attention to this, because this not only it shows how we repair this box culvert in Phoenix, but it really pay attention to the economics advantage of this system as well. So let me, I'm going to share this. Let's see if we can get this going here. Share with you. Oops, I guess I have to do something else to show that screen. Share. There we go. Okay, so here we go. Let's just watch this thing together, this video, and see how.
Our client for this project was the Salt River Project. SRP is a major utility company that has delivered water and power to central Arizona for a century. The Western Canal is one of 5 major canals in Phoenix that supplies water for both irrigation and municipal use. In the late 1960s, Arizona Department of Transportation constructed the twin box culverts to carry the canal water under I-10. An inspection in 2017 revealed that the reinforcing steel in the soffit of the culverts was corroding, causing cracking and spalling of the concrete. The consulting firm WSP was retained to evaluate the structure and recommend a repair strategy considering serviceability issues such as stability, durability, and cracking, plus strength of the culvert to carry the interstate freeway traffic load safely. WSP recommended a combination of repair of corroded regions with cathodic protection and the use of carbon FRP for strengthening of the soffits. Based on previously completed successful projects, such as the repair of a 90-year-old riveted penstock and several bridges in Phoenix, SRP and ADOT decided to award the contract to the team of FRP Construction and QuakeWrap Inc. as a design-build project. The engineer of record provided a performance spec, and it was up to each FRP manufacturer to provide the design subject to the EOR's approval. Strengthening of the box culverts was achieved by a single layer of unidirectional carbon fabric. The fabric steps were overlapped by 2 inches along the edges. Although this provided significantly higher strength than necessary, the complete coverage of the soffit would provide an impervious protective layer that will delay corrosion of the steel in the soffit. To facilitate the construction, water was diverted into one cell while the adjacent culvert was being repaired. Construction included installation of anodes before the concrete was patched. 12-inch by 12-inch chamfers were also built along the edges to increase the negative moment capacity of the slab. The 24-inch wide carbon FRP fabric was saturated with epoxy in the field and installed, and a top coat was applied. The project was completed over a period of 3 months during the low flow season. The engineer's estimate for replacement of this culvert was $25 million and would have resulted in significant disruption of traffic. The repairs were completed at a total cost of only $1.3 million over a 3-month period, with zero traffic disruption or control. We thank the support of our partners on this project that are listed here.
Yeah, so you saw this project. Again, we ended up because the engineer of record wanted to enlarge the fillet, so we went from 3-inch or 6 by 6 to a 12 by 12, as you see here. The guys, this actually in this project ended taking most of the time, went into enlarging this fillet at the corners, which really, it's debatable whether we really needed it or not, but that was done. And then, this cathodic protection was another thing. But also, I wanted to draw your attention to this, that in a structure like this, when the slab is damaged, you have to, with the wet layup system, you had to patch the slab and get it smooth before you can apply the fabric. And to remind you that strength-wise, we didn't have to put like these 24-inch bands of carbon fabric. They could have easily gone every 30 or 36-inch on center, and that would have given us plenty of strength. But we wanted to protect the soffit of the slab with a layer of FRP, so there's no moisture penetrating into it as a waterproofing membrane also. And that's why we decided to go put these 24-inch bands with 2-inch of overlap along the edges. So as you see on the right, when the job is completed, there is no part of this slab that is exposed to the elements. So that's it. Now, the code again, looking at this ACI 440, I have taken a few pieces out of it. When you look at, if you get a copy of this code, they have worked out examples for flexure, shear, axial load for columns, all of those. That it has actually so many examples at the end of it worked out, both in US customary units and SI, and you can follow these easily. I've just taken a few snapshots of it just to show you that the kind of stuff that you see. So one of the things, for example, is that, for the material properties, if you make these coupons in the field, for example, you do 5 tests here, and get the average of the test, and you see the thicknesses vary a little bit. So in this particular example, they have a thickness that varies from the smallest one being 0.053, and then the thickest one being about 0.069. And you can expect this kind of variation on a sample because it's done by hand in the field. So this is kind of normal. And then the load that it takes to break that. This is for a 2-inch wide. They were all 2-inch wide strips. So for those 2-inch wide strips, it took this kind of anywhere from 17.8 kip maximum to the minimum of 16.4 kip to break the sample. There are this is again these material properties you have. So the manufacturers list these properties in their product data sheet, and they basically include the thickness of the material, the tensile strength, strain at rupture, and then the modulus of elasticity. And depending on the type of material and how it is manufactured, the one that you see on the left is a representative of what you would like a wet layup product that the crew would be building it basically in the field. on the right, this system B represents a material that is made in a factory. It's a pre-cured unidirectional laminate. These, as you can see, they get much higher. Like the tensile strength is 380 ksi versus the one that you make in the field, which may be about 170 or 180 ksi. And the modulus of elasticity likewise. For the ones that are made in the field, they are lower. When you make it in the factory, the modulus of elasticity is like almost double the other one. So just keep these things in mind as you do that. And then again, these are just like taking some. I don't want to take a lot of your time going through this, but these are the steps that this is for comparing the two different systems. But then next we get into, this is one of the design examples from ACI 440. So, and they have multiples of these. So in this case, for example, this is a beam designed for flexure, which means the same thing that we would be doing here for this uh, culvert. We actually take like a 12-inch or 1 foot wide section of the slab and design it like a beam. So in this case, this beam that they give the designer is a 24-foot span, 12-inch wide by 24-inch deep, and they're applying 2 layers of fabric. You see, they have one layer and then another layer on top of it. So there's 2 layers, and the 5,000 psi concrete, 3 No. 9 rebars originally, and so you go through all of these steps that they tell you in this code. You follow one by one to get all of your design done. One of the things that the ACI 440, even though there are a lot of laboratory tests, have shown that you can have, in the studies that have been done, people have shown that you can get the strength of these beams to go 3 times as much as the unretrofitted one. But the code, it has taken a conservative approach, and so you can only increase, or you're allowed to increase the flexural capacity by only roughly in the order of like 30 to 40% with some of these checks that you see in here. So for example, the second one from the bottom, they say that the unstrengthened moment limit should be 1.1 dead load plus 0.75 live load. So you cannot have anything less than that, and so those limits kind of guide you such that you can't say I'm going to increase the capacity of this beam by 3 times. You can only increase it by roughly 35 to 45, maybe in some cases to 50% based on these factors or facts that you have to check. And the one, so the summary of the material properties that you would use in your design, the most important ones are the thickness of every ply, like this carbon fabric, maybe 0.04 inch, its tensile strength, the modulus or the strain at failure, 1.5% strain, for example, in this case, modulus of elasticity. And what we use, what I really like to use in most of my design is that I take that tensile strength 90 ksi and multiply it by the thickness of the laminate, and I look at the breaking force. So this, in this example, for example, this gives me 3.6 kip per inch. And that, as a designer, it should really give you kind of a good rough idea of how this fabric, for example, would compare with, let's say, a number 4 or 5 or 6 rebar that you would be using, in the field. Okay, so this could be a guide. This last one, the breaking strength, is something that I personally like to like to use a lot in my designs. Well, and then here are, again, some of these more information about these designs that go through. This is just, again, this is one of the tables that you see that it has 14 parts to it. I don't expect you to be able to see this, but just realize that you go through these one by one. They show you how you do it. And at the end, you come up with your design. And here you see, like, they have step 14. So you just do the same checks. You can come up with your wet layup design. So That is one approach for, as I said, for repair of uh, your, repair of a culvert or slab. But the next one that I want to show you is, is to how you would use our, this is our SPiRe Plus panels that we have introduced, since last year, and we've used a lot of these on different projects. So in this case, let's just compare that. We didn't have this, by the way, in our arsenal when we were doing 3 4 years ago when we did that Phoenix project. Otherwise I might have recommended to use this product, but instead we went with so how this product is done. One of the benefits of this is that you do not need to do any surface prep. These these basically, like, let's say if you have a bridge girder that is damaged. This happens to be a oops. This happened to be a bridge from in South Carolina, that you see this was severely damaged. So in a repair of a girder like that, you these panels, the SPiRe Plus panels, they come in 3 feet wide, as you see here in the next slide here. Uh, Here they are, 3 feet wide by any length that you want. And the test that we have done on these, they show that these panels are equivalent to like a number 5 grade 60 rebar at a spacing of 2.5 inches. It's really a lot of steel. So in terms of flexural strengthening, this is far more than you would probably need. You don't need to add any additional steel. Just the T profiles of this SPiRe Plus act as your reinforcing element. And because the whole product is grit coated, it bonds really well to concrete, so you can develop those high forces. So let's say in a case like this, you would take those panels, and we also have these 90-degree angles that you see. Let me hold one of these. Like these 90-degree angles, they come in, in a length that you want, and you can connect, put these like so at the corner of your panel, like this way, and put another one, put the next one over it this way, and you create like a box shape of any formwork that you want. You can make it in the field. Okay, so um, and then once this is bolted to the side of the girder and maybe a couple of bolts at the bottom, then you fill the annular space with grout and you're done. The one on the lower side of the slide, this is actually an ongoing project we started last week. It's at the port of Long Beach, and these are for Carnival Cruise Lines. 4 of these dolphin structures that we are repairing, the piles are being repaired. The steel piles are being repaired with our Pile Medic and our patented shear wrap system that for load transfer without any welding. So that's for the piles. And then the pile cap, this portion is being repaired with this SPiRe Plus. So you saw this. This is kind of like the equivalency of these. And if you uh, if I show you let's look at the one of these. So let's say, for example, if in this case, we were going to, you notice that here, by the way, I took this picture of when our guys were prepping the slab by uh, troweling a grout to get, the concrete on the slab was rough, as you see here. So we had to first apply some concrete or cementitious material over it to patch it and make it smooth before we could apply the fabric when we did that project in Phoenix. But if we were going to use our SPiRe Plus system, that rough surface is perfect for it. We don't want a smooth surface. So if we were going to do that project with the SPiRe Plus, we would take these 3 foot wide bands. Remember, the culvert was 14 feet, had a span of 14 feet. So we would take these panels, cut them in 14 feet lengths, and they come in 3 foot wide. So we would put them 3 foot by 3 foot by 3 foot, one next to each other. And as you see in the middle of this slide, we provide a rubber sealant that you put on the overlap joint. The overlap joint, by the way, I can show you here. You see, as you see here, this is like a 4-inch overlap joint, and you see that when they go over on top of each other, it becomes nice and flush. uh, they're designed to give you a flush finish surface. But we put that sealant in between these, and then in this case, it might have taken, because the length of this was, for example, this repair of that culvert in Phoenix was 380 foot long. So you divide that by 3 feet, and you see that you need maybe about 130 or so panels of 3 foot wide to cover the whole length of that. Okay, so that it would have been much easier. Of course, it does take a little, because this is 1.5 inch or 38 millimeter thick. So we mount that with a little bit of a gap between. So when you pump the grout with your grout pump, when you pump the grout, it would flow over these. But uh, it would take a little bit away from the flow capacity of this, but maybe, I don't think, like in this case in Phoenix, I don't think that would have been a major problem. But the repair would be much faster, of course, and then you get a lot of strength out of this system. Uh, we don't have, obviously the one project in Phoenix, as I told you, for that culvert, we didn't have this SPiRe Plus available then, but we have used it on other slab projects. Like this is a project we did in North Carolina, where this slab was severely corroded, as you see in the upper left. And then on to the right of it, you see these 3 foot wide panels being uh, connected to the underside of the slab. And in this case, the contractor chose to drill a hole from the floor above and then pump the grout from above to fill that void between the SPiRe Plus and the slab. And then on the right side, you see the finished project, very nice, smooth finish. And not only that, but now you have this, point, like this is about 0.2 inch thick layer of FRP that forever will be protecting that slab from moisture and future deterioration and corrosion. So uh, we have grout ports, as you see here. These grout ports, they are connected to, if you want to put it on the sides of your girder or on the bottom of it, you can put these, and then with these cam locks, they can connect, and uh, you from here you inject the grout, and then once it is done, there's this guillotine that you put in here, so you stop the backflow of the grout, and then you disconnect your pump and go to the next grout port and continue doing that operation. So we're kind of like running to the end of our time. So I wanted to remind you again, please, that we have a new look at our page. It's now Infrastructure Repair Live, but the address is shown here, so you can go to through our PileMedic website, go that. And if you have any ideas or questions, especially now that we have opened the field to all of these, not just marine, if you have any ideas for topics to cover, please let me know. We will be doing some things about pipes and chimneys and a lot of other interesting projects that are ongoing. Maybe in the coming months, we have a lot of ideas to do. But if you also have anything particular in mind, please let me know. And I think we're coming to close to the end of our time, so I appreciate your attention, and hopefully we'll see you in next month. I'm on Saturday. A personal note: on Saturday, I'm going to on a trip to China for 2 weeks. As some of you may know, we opened the QuakeWrap Asia branch in China January when I was in China, and we just completed our first bridge repair project in China last week, repairing several piles in a water crossing for a bridge in near Shanghai. So I'm going there to meet with some of our potential clients and visit the job sites and so on. And look forward to seeing you again in a month or so at our podcast.